Today's part is about conservation of energy. So previous class we learned about work done, principle of work done, and how to use that principle in order to solve for things like forces, acceleration, and so on. So we're going to use a different idea called conservation of energy, and then we'll have to define the energy for a spring system and energy when things are moving under gravity. So gravitational and elastic potential energy. And then the important thing about conservative and non-conservative forces, which will help you to distinguish which principle to apply given a problem. So let's get started. So what are conservative forces? So when the work done is independent of the path taken, it is called a conservative force. Examples of conservative forces are gravity, and then spring force. Right? So why is gravity? Well, if I take an object and move it from here to here, the work depends only on the displacement or the final position. So it's going to be mg times final position minus the initial position, right? I could move it this way, I could move it this way, I could move it that way. No matter how I move it, it only depends on the difference between the potential at those two places, right? So that's why it's conservative. Same for spring. If you stretch the spring, it doesn't matter how you stretch the spring. You stretch it fast, slow. What matters is that it goes from initial position S1 to final position S2. The work is going to be independent of the path or the velocity or anything in going from place A to place B. A non-conservative force, on the other hand, is a force where the work done depends on the path taken. So work depends on the path taken. An example of such a force would be friction, especially Coulomb friction. So we call it Coulomb friction. We know Coulomb friction to be mu n times displacement, right? Okay, so clearly if you go from point A to point B on the table, say, if I move the particles in a straight line, the work is going to be x. If I move it, if I go there and come over here, it's going to take more work because now it depends on the path taken. So that's an example of a non-conservative force. Okay, I'm going to define potentials, and which will be used to use another principle here, which is called conservation of energy. So gravitational potential energy. So just like when you find the work done, you need to take data with respect to a datum or an origin. In this case too, you need to look at a datum. So I'm going to fix this to be my datum line about which I'm going to measure the potential. So if the mass is on the datum, its potential is 0. If the mass is moved down, well, gravity is clearly this way. If the mass is moved down, we say that the potential is negative. It's the weight times the displacement. So this is y. W is the weight or mg. If we take the mass and move it up like so by distance y, then we say that the potential is positive. Okay, note that this is exactly opposite to what we had defined for work done. When we took an object and we moved it down, mg acts downwards, but our y is measured upwards, so the net work done was sorry, my bad. Y is downwards, so it's positive. While when you move things up, the work done is negative because the force is down while the displacement is up. So when there's the force and displacement have different directions, you have negative work done. So work done is negative but potential is positive. Work done is positive but potential is negative. Don't get confused. Just remember one of the two, and then for the other one just switch the signs. So that will become slightly confusing when we look at both the principles, work done and conservation. But don't worry about it right now. I'll remind you once we get to those problems. So elastic potential energy. I'll denote that as VE. So when the spring is unstretched, S is 0, the potential is clearly 0. If you stretch the spring like so, then the potential is a half ks square. You know what, let me put S equals S0, just indicating that it's a non-zero length spring. So now this is S0, this is S, this is S. So now the work done is S, K times S minus S0 square. And then if you compress it, so no matter what you do with the spring, you compress it or stretch it, the potential is always positive. Okay, again, just note that this is exactly opposite to our definition of a work done. Work done, when you stretch it or compress it, the work done was negative. You can turn back a note and see the note. It will be negative. So the potential is always has the opposite sign to that of work done. Okay, last thing before we start solving problems. So there's something called principle of conservation of energy, okay, which states that T1 plus V1 is T2 plus V2. T is the kinetic energy like we had defined it earlier. V is the potential energy. So when you take the potential energy, it is to be the sum of all the potential energy. It could be spring, damper, spring, gravity, and so on. 1 and 2 are instances of time. So for example, at the first instant, maybe the spring is unstretched. And when you stretch it, it's the next instant. So you take the initial energy. The principle says that sum of the energies before and after are the same. Okay. Now this equation is only true for a conservative system. Only valid for conservative system or conservative forces. The moment you see dissipation like friction, you should not use this principle. If you still want to use this principle, then you can modify it slightly. T1 plus V1 plus the work done by the non-conservative force equals T2 plus V2. This is true for non-conservative forces or systems. Okay, this is the work done by non-conservative forces. So this is the most common equation you see in this particular chapter. The other one is this one. So what it's saying is that if there's friction, then clearly the initial energy, kinetic plus potential, is going to be greater. If you ignore this, the work done, then that energy is going to be greater than the final energy. So if you move a block from A to B, then because of friction, the energy after the motion is going to be less than before, unless you account for the non-conservative forces, which in that case of the block moving is the force of friction. Okay, let's just put everything I've said here into some problems. Okay. Okay, so if the 20 kilogram cylinder is released from rest at height h equals 0, so this is the height. Determine the required stiffness K of each spring so that its motion is arrested or stops when h equals 0.5. Each spring has an unstretched length of 1 meters. Okay, so essentially what's going on is this system is the block is over here, height is 0, it's let go. Again, it's going to probably bounce out, but we're not interested when it bounces that way, because it's in the instant when it is stationary. So we want to find what that spring stiffness is, such that this block would be at a height of 0.5 meters from the horizontal position. Okay, so let me draw that if that makes it easier. So initially, that's how the block is going to be, and finally h is 0. Okay, so this is 2 and 2, 2 and 2, that's 0.5. Okay. Okay, so first of all, the question is, could we do this using F equals ma? I believe you can. This is a problem of static equilibrium. Where the mg is just, where the force due to gravity, mg just equals the force due to the spring. You should be able to do it using just statics. You don't need to know anything about this course to solve this problem. But you could also do it with tools from this chapter, because the system essentially has certain energy when it starts off, and that energy, so initially the energy is actually potential as well as gravitational, sorry, only potential, and then when it drops off, it gains potential energy and also, it decreases potential energy and increases the spring energy, and that's how it's initially used here. So you could use that too. So let's use conservation of energy, just because there are no dissipative forces. So this instant is 1, this instant is 2. So I write T1 plus V1 is T2 plus V2. So I need to write the kinetic energy T1 when the block is in that position. Right? The initial kinetic energy is what? 1/2 mv squared. But what's the velocity when it's at 1? It's 0, right? So the initial energy is 0. What's the initial potential energy? V1. So note that there's gravity involved, and then there is of course the spring energy. But in order to find the energy due to gravity and that due to springs, if you notice here, I chose a datum. That's very important. So we need to choose a line about which we're going to measure the energy, and that could be any line you want. So what makes most sense in this problem is to use this line as the datum, which is also this line, right? So when the system is on the datum, the potential energy is, due to gravity is 0. So 0 due to gravity plus what's the energy due to the spring? Half k. First of all, the sign is positive, so it's half k, and it's going to be the net stretch in the spring in this position. Then it's over here. So what's the stretch? So it's 2 meters is the initial length. What's the unstretched length? It's 1 meters. So it's 2 minus 1 squared. Okay, but there are 2 springs, and they have the same stretch and same potential. So this is going to be twice. So this is due to spring. Okay, so that is all the energy T1 plus V1 when it's initially at that position shown there, number 1. Now we need to write the same thing for number 2. So what's the initial kinetic energy? It's 0 because the block comes to rest. Okay, what's the potential energy due to gravity? It's mg times the drop, which is 0.5. Is it positive or negative? It's negative because if you look at the notes, when you drop down, it's going to be negative. So gravity. And then finally, what's the energy due to the spring? So it's going to be 2 times, because there are 2 springs, times half times k times the new length of the spring minus the unstretched length. So what's this length? That's the new length. How can you find that? Pythagoras theorem. So if this is 2 and this is 0.5, this is 0.5, then that's going to be 2 squared plus 0.5 squared. What did you get? 2.06. Okay, 2.06 meters. So it's going to be 2.06 minus the unstretched length, which is 1. Okay, so let's see. We have this equation. K is unknown, but M is known. It's 20. G is 9.81. So you have pretty much everything except K, and so you can solve for K. So what I got is 773 Newton per meter. Okay. Okay, so the ball has a weight of 15 pounds. This is 15 pounds and is fixed to a rod having a negligible mass. If it's released from rest when theta is 0, so it's clearly released from this position. This is the initial position. We'll call that position 1. Determine the angle theta at which the compressive force in the rod becomes 0. So let's call this the final position, or the position where we want to find the force where the position when the force in the rod becomes 0. So clearly there's going to be a force. We want to find theta such that the force is 0. So a problem like this can be done using x equals ma. If you set up this equation, so what you need to do is draw the free body diagram of the system, find the force, and once you find the force, you need to find the conditions under which it's going to be 0. That will give you a solve for a theta. So as I said, can be done using F equals m. In fact, we will actually solve it as if it's F equals ma problem till we reach a certain point of time where we'll start using conservation of energy. So I'm going to draw the free body diagram for the rod at a generic position theta. Let's say that the force F is so. Okay, I do not know the force direction, but I'm just going to assume it's that direction. Mg is downwards. The angle theta is also this angle. Right? Now, since it's moving in a circular fashion, I have two choices. I could use, well, I do not want to use rectangular coordinates because it's moving in circles. So it could be either polar coordinates, r theta, or it could be nt coordinates. Okay, both those coordinates will work for this problem because it's moving in a circle. If the position is usually a function of x and y, I recommend vt, nt coordinates. If it's r theta, then you want to use clearly r theta coordinates. So in this case, I'm just going to use nt coordinates. Okay, I would need to write the equation of motion, because if I do not write the equation, I will not have an expression for the force. So equation of motion. So far it looks like I'm using F equals ma to solve it. So I'm going to write the force equilibrium in the n direction is mass times acceleration in the n direction. So the force in the n direction is simply F. Since it's acting in the direction opposite to n, it's negative F. And then there's mg cosine theta. So mg cosine theta is the force acting in the n direction, but its direction is along the n direction, so it's going to be positive. And the acceleration in the n direction is mv square divided by the length. Right? I would write v2 because this corresponds to the final position. Velocity when f is 0. Okay, so what I'm asked is find theta when f is equal to 0. So I know m, I know g, I know l, I know m. I do not know v2. So as long as I can solve for V2, I can then find theta. Now to find V2, I could use F equals ma. The way to proceed is, there are two ways to proceed. One is you write the other equation for this particular problem, which is in the t direction. So F equals ma in the tangential direction. That'll give an expression for acceleration in the tangential direction. Integrate that expression, it'll give you V2 and solve this problem. So you do not have to know anything about conservation of energy here. The other thing you can do is, you can try to use the conservation of energy from 1 and 2 to solve for V2, and that's another way to proceed. So two ways to do it. So two methods. One, use Ft is mass times At, get V dot, and then integrate to solve for V2. The second method is the one which I'm going to do here, is use conservation of energy. But you should try it. So I'll do it method 2, but you should try using a method 1, see if you get the same answer. So this one says T1 plus V1 is T2 plus V2. Okay, the initial energy in position 1, the total energy is, so the kinetic energy is 0. For the potential energy, we need to choose a datum, right? So I'm going to choose this to be the datum. So what's the initial potential energy? It's 0, because the object, the mass is at the datum, equals the final kinetic energy, which is half mv2 square, that's T2, plus the potential energy over here. So this is the drop in height. The drop in height is, it's going to be L minus L cosine theta, right? This is L, and this distance is L cosine theta. So the difference is going to be L minus L cosine theta. So mg L minus L cosine theta. What's the sign on that? It's negative because it's dropping down with respect to the datum. So V2 square equals 2G. I'm going to remove this, plug that L out. Okay, 2GL1 minus cosine theta. Let's call this first equation, F equals ma equation is 1. The next equation is 2. So I'm going to put 2 in 1. To get minus F plus mg cosine theta equals m divided by L times 2GL. Okay, so the L cancels off. F is 0. M cancels off. I'm left with what's that? Yeah, just let me just keep it as V2 square so I can easily put it into, yeah. G cosine theta equals 2G minus 2G cosine theta. So cosine theta is, I think it's 2/3. So theta is 48.2 degrees.